You know, there's a couple on there that, by gosh, they are legitimate.
Are they really? I'd like to welcome everybody again and thank Keith for rearranging the room here, wherever he is. I guess he's not here right now. So at least we can breathe tonight. With that wind,
we had come in the back window there last Tuesday. That's probably a good thing we were all huddled up, because that was anyway, we're going to pick up where we left off last week, and we're going to talk about the TNC, the terminal, a little bit about signals on both sides of the TNC, and then from there we'll start getting into the actual packet protocol. We basically stopped with this slide. Before we get into it, are there any questions on what we covered last Tuesday night?
You have some other books, Bill.
Oh, we need some additional handouts. Is that what you're asking?
No, the book. I don't know where you had enough books or not. Binders?
Oh, binders.
Yeah, we'll get some more. Who needs? How many binders do we need?
I need a book too, please.
Oh, okay. Yeah, Keith made a bunch of those copies.
Okay. Well, Dick, I see you learned your lesson. You're not sitting in the back of the room like last week.
You're right.
I could see snow blowing around you back there, and I was up here sweating at this end. Couldn't figure out why you were all bundled up back there. Okay, well, we'll go back over this slide again. The purpose of this slide was to give you an idea of how packet works, in the sense that it's little packages of information that are sent between you and whoever you're talking to, and vice versa. And your little packets of information are interspersed with other people's packets of information. So we're doing what's called channel sharing. Now, let's say that this is one station. We didn't really go into this last week, but let's say this is one station that is talking to Station A, Station B, and Station C. Okay? Last week we looked at this as three stations. A was talking down here to A, and B was talking to B. Okay? But actually this fellow here at this location could set up what you might call a logical channel to Station A. In other words, he connects to Station A, and anything that he sends on this, what's called a virtual channel. In other words, it's not a separate channel because you got other things on this same channel, but virtually or logically it's a channel. Anything he sends with the A designators will only show up on this fellow's screen. Okay, so as far as these two people are concerned, they have a channel between them. Anything he types will appear here, anything he types will appear here. Likewise, if this fellow sets up a second virtual channel to user B, then when he moves his keyboard, we'll get into this in a minute, but when he moves his keyboard to this logical channel or virtual channel, anything he types on it will only appear here. He moves his keyboard back to this logical channel A, anything he types here will appear over here. Question?
Is that done by the logic of the computers at the nodes? In other words,
No,
it all goes over the same radio frequency.
yeah, the nodes just pass the packets on. And we're going to cover that in a lot more detail later on when we talk about how the network works. The nodes see this packet coming in, let's say on 145.01, and it resends them out on 145.01. Okay? Well, this station hears the packets with the A addresses on it, and he pulls it in and puts it on the screen. He hears these packets going out of this node too, because all of this is on 145.01 in this example. But he ignores these. He says, well, those aren't for me.
What's doing the ignoring?
The TNC.
Choosing.
The TNC at the station. We're going to cover the TNC here in a few minutes. All the logic is going on in the TNC. So the TNC is listening, and if he hears packets coming in error-free with his address on it, he pulls it in and does whatever he's supposed to with it, puts it up on the screen or whatever. And we're going to spend 2 weeks talking about what he does with it.
But those
Question.
packets for B and C wouldn't come out of that node and towards user A at all.
Yeah, they would.
They,
This could represent a station sitting on Mount Evans.
so
And this is in Denver, and let's say this user C is in Denver, and all of this is on 145.01. This could be Colorado Springs, Pikes Peak. So this user in Colorado Springs connects to this node. He tells this node that I want to talk to, let's say, Denver. And once this node establishes contact on this logical channel, this is all this is on 01. These are radios. This user here gets a message saying you are now connected to Denver, and he tells this Denver node on Mount Evans, connect me to user A. And the TNC hears this connect request from the node on Mount Evans and says, here I am. This node tells this node, you got it. This node says, you have him. Now, every time he types something on this logical channel A, it goes to this node, and this node sends it out. This TNC and anybody else that's sitting here all hear these packets coming out.
whether they're A, B, or C.
Whether they B or C. Now, if it's A, TNC, station A, TNC, and he hears the A packets, he will pull them in and do something with them. If he hears the C packets or the B packets, he'll ignore them. He says, well, those aren't mine. The user here, station A, anybody else here, can actually tell us TNC, I want to hear all of this stuff. But if you're talking to somebody and you're copying all this other stuff, your screen gets kind of busy. And there's different levels of what you can monitor. And there's a monitor all, for example, where you see everything going on. You might use that in troubleshooting, which we'll get into later on. Why can't I connect to this guy, or why does he connect to me, but he doesn't know he's connected to me, but I know I'm connected, da-da-da-da, see? And you'll be using a lot of these different levels of monitoring for troubleshooting when we get into that. So anyway, this node is receiving the packets. Go away. That's one of those bits, bugs that gets in the bits there. But anyway, this user here has set up 3 logical channels. And since we have something wrong here right now, Colorado Springs and Boulder cannot hear each other. So when this user here says, okay, I want to connect to Denver, and then I want to connect to this guy, everything works fine. He gets this logical path set up. Then he says, okay, now I want to connect to Boulder, and I want to connect to station B and station C. Normally this node would set up a logical channel here, but it's gone. So he tells Denver to connect him to Boulder. And when that happens, this fellow's advised of it, then he tells Boulder, okay, I want you to connect to B, and I want you to connect to C. Okay?
Hey, Bill.
Yes.
Are there repeaters or straight simplex?
This is all straight simplex. There are.
You got to have enough power to come from Colorado Springs to Denver then.
No, you're only talking to Pikes Peak.
Oh,
You're telling Pikes Peak
okay.
to connect to Mount Evans,
That's what I want to know.
and you're telling Mount Evans to connect to this guy. You've told Colorado Springs to connect to Boulder, only he knows he can't do it. Remember we talked last week about how these nodes all put out special IDs. And if this node in Colorado Springs hears the special ID out of Boulder, he will put it in memory so that anytime anybody wants to connect to Boulder, he says, okay, I'll do it. Now, let's say we have a problem in the path here, and these special IDs are not getting here. But the special ID does get here. This is all 145.01 in our example. Boulder puts out the special ID. It doesn't make it here, but it makes it to Denver. Denver puts it in here, in his routing table, in his memory. And then he tells Colorado Springs who he can connect to. So these nodes are always updating each other as to who they can hear and who that they can hear can connect to who, sort of thing. So it's kind of like a tree. They pass this information down. Okay?
So the people in Boulder would be on 145.01 and the people in Colorado Springs would be on 145.
Everybody on 145.01 in this case. 145.01 is your main, what they call NetROM network. You can go clear to California on 2 meters through these nodes. Now, we have other nodes that allow you to go over to a different frequency. You could come into with several nodes here in town and go out on 10, go out on 20, go out on 18, and then repeat the same process on HF. That's how, remember the example where I played the tape recording of the guy on the tanker that I had connected to earlier? In that case, I was sitting on 145.01. I connected to a node called WG0N-7, and I told him to call the tanker on 18.103 megahertz. So now the node's calling the tanker answers back to the node tells me we're now connected. Anything I send into the node on 2 meters, he repeats out on 18 and vice versa. Those are called gateways, and we're going to cover all this stuff later on. Yes?
I'm confusing myself a little bit. The difference between a node and a user is basically computer software, right?
Yeah, a node is basically a TNC or a TNC in a computer that acts as a switch, as opposed to a TNC, which we're going to cover in a minute, which is a way of you sitting on a keyboard and sending data out on the radio and vice versa.
Most TNCs could be set up as a node, right?
You have to, if you're going to change the TNC itself, you have to put a ROM in it, which converts it. There are TNCs that have node capability. This right here is one of them. This is actually like 2 TNCs in one box. So you could put one on 18 megahertz or HF, put the other one on VHF, and then you could allow the two to intertalk. So if somebody comes in here on one connector, they go out on the other connector.
Is there time delay? It's not like a voice repeater where it's...
Yes, there are time delays based on traffic.
Isn't this whole thing time?
Yes.
Time multiplied.
Yes. This is what, when we talk about virtual channels or sharing a frequency, it's time division multiplex is what it is. This is his time, that's his time, that's his time, that's his time, etc. So you're actually taking a shared channel and splitting it up into chunks of time. And if you're not using it, somebody else gets it. And then you wait, and then when you hear a clear spot, you jump in and send your little packet. So it behooves you, if you're talking to somebody and you can hear them direct, you don't have to go through one of these nodes or something to go off on your own frequency, so you don't have to share it.
TNC, isn't it?
Pardon me?
The time share is automatic in the TNC.
Automatic and the TNC. We're going to get into that in just a bit.
If you were going through the node to an HF, which is 300 baud rate, does that node computer convert from the 1200 baud to where
Right.
you have to do?
Right. It converts speed.
So you stay, if you're on 2 meters, you stay.
You stay at 1200. It buffers and then out at 300 and vice versa. We'll cover that in just a minute. I saw another hand.
When you went out to the tanker via the node, via the HF node, you said you instructed it to connect on the 18 megahertz channel. Then you had, by virtue of some keyboard entry, you had some control over exactly what frequency that node sent that out on.
Yes, all nodes, usually when you log in, the node will tell you what ports he is on. In other words, I have a port on 10 meters, I have a port on 2 meters, and these kinds of things. Most TNCs, when they're set up, they let you know what the frequencies are. And we're going to cover this in real depth in a couple of weeks, where you go into node and to a node and you find out who it's hearing and who's where and what it's hearing, and then from there you can go. We're going to demo all that over here, how to do all that. Right now, this is an overview, so I don't want to get very deep into it. Another question.
You said that I guess the nodes are always telling each other the Every so many seconds they say I'm still here.
Yes, yes. That's a sysop parameter that the sysop sets. I think the default is every half hour on the net ROMs and the VNets. And how about the cams?
15.
About 15, okay. They use a different, I don't want to get too deeply into this. The cams don't update each other like that. We're going to spend a lot of time in this whole area. But first you have to suffer through how the protocol works, the boring, dry stuff, and then we'll get to the good stuff. Remember, this is like the mission. You've got to hear the sermon if you want the meal. So I don't want to get too much deeper than this right now.
Okay, so if the packet is taking an alternate route, can it still be a logical channel?
Yes, it sure is. I don't want to get too deep into it.
Can a node go down while you're in the middle of a transmission and lose it?
Oh, sure. Doesn't happen very often, but
9 out of 10 times it does.
see, remember I told you last week was going to be a quiet week because Les wasn't here.
Somebody has to keep Bill awake. That's what he said.
Yeah. Even more so when you're on HF, because this path could fade out. This could be Boston, this could be California, and all of a sudden you're not there. But there's all kinds of ways that's taken care of, and we're going to go into that as to what happens when that does. It's not a disaster at all. Anyway, on most of your TNCs, you have a parameter. We're trying to cover the various parameters as we cover the topics here that are related to the topic. You have a parameter on most TNCs called users. And what that says is how many people can connect to me, not how many links can I set up. This fellow here could have users set to 1, but he's got 3 channels going to 3 different users. Okay? Now, the way to look at this is most TNCs allow you to have up to 10 virtual channels. In other words, I connect to Joe Blow on channel 0, or my first channel, and somebody connects to me on channel 1. So I tell my TNC, okay, send this out on channel 1. Send this out on channel 0. See? And these people don't see each other. They only see me, and vice versa. That's why it looks like a for real channel, even though you're all on the same frequency.
You're on 0 and 1's transmitting to you. Do you know it?
Mm-hmm. Depending upon, and we're going to show examples of this, depending upon whether you're running a dumb terminal or software that has Windows, etc. The key point is, when you're using your TNC, you always want to be on your logical channel 0. Now, some TNCs call it streams. I think the MFJ calls it streams. The PK232, PK88, they call them channels. If I have users...
Are those all, are they numbered or are they all in A, B, C, and D?
That's a good point. A lot of the TNCs call them channel 0 through channel 9. Other ones call them streams A, B, C, D.
MFJ.
Yeah, how many channels can you have on the MFJ?
I think 9.
9? Okay, and the 232 is 10, but it's around that. The whole point is, if you're not used to multi-connecting, because this is a little bit of an art depending upon how you're doing it, you always want to be on your lowest numbered channel, your stream A or your channel 0 or whatever. If you're on channel 1 and you got users set to 1, somebody can connect to you on your channel 0. The way to look at it is, if I say that I have users set to 4, that means my first 4 channels, logic channels, are available for a connect. Logical channel 0, 1, 2, and 3, or A, B, C, D. Okay? So when somebody's going to connect to you, they're going to come in on your lowest numbered channel. And the next guy connects you on the next channel above that. Well, like I say, if you're sitting on this channel, you got users setting to 1, you're on channel 1, that means logical 0 or stream A is available and somebody's going to connect to you. I've had it happen so many times where I'll connect to somebody and I'll be watching his other channel, his other virtual channel, because I'll have my monitor on where I can see these, and he'll say, somebody's connected to me, I don't know how to talk to him. See? So that's called users, and that's the way it works on most TNCs. Now, one thing I want to mention, and I'll pick up your question, I'm not familiar with MFJs. I fool around with CAMs, and there's some other ones out there, so I'm looking for help when we cover all these kind of parameters.
As far as I know, all TNCs work this way, but I don't know that for a fact. I know the CAM and the 232 and the PK88 work this way. Question?
Yeah, if you connect to somebody, I'll say you're connected to two, so you're using up those first two channels, then say the guy on channel 1 stops communicating with you, then does the other one then drop to channel 0, or...
No, you always stay on whatever channel you set up. You always...
Then somebody could reconnect on your 0.
Yeah.
Right?
Mm-hmm.
Would you know it?
Oh yeah, because your screen will come up and tell you, you know,
So
channel 0,
you could be
da-da-da.
on- You could be on 2 or channel 1, be forced on a channel 1 and still get back to
Mm-hmm.
channel 0. Okay.
Yeah, because like I say, you can look at these as telephones. I have 3 telephones sitting here with 3 sets of wires going to a CO. And I have a feature where it's called rotary, where I have one number and they'll come in on the first phone, and if that's busy, they'll come in on the second one. Okay? It's kind of like that, except it doesn't rotor. It always comes in the first one, and if I allow 2 connects, it'll look for the second. If I allow 3 connects, it'll look for the third. It works down that rotary. Okay? Can you hear the questions okay? Or do I need to?
Probably help to repeat it.
Okay. All right, let's move on here. We're getting a little deeper than I really want to at this point in time. Can I have the next one? This is kind of where we left off last week. We're going to spend some time talking about the TNC, the terminal computer, a little bit of time about the radio. And then from there, we're going to go into how these packets move around in this network. In other words, I'm here in Denver, and I go into this network, and I come out in California and connect to this guy. And when we get into the protocol, you'll get a better feel when we say connect and disconnect what we're really talking about. So we'll spend some time at length talking about all these bits of information flying all over the place. You know, it's like popcorn popping. You know, it's amazing it comes out the other end where it's supposed to. And then from there, we'll actually talk about the components within the network. The first thing to mention is this guy right here, the terminal. You do not have to have a computer to run Packet. A demo terminal that you can get for $10, $20 works fine. I used one for years, never had any problem. So you don't have to, like I say, spend a lot of money to get into this game. Most people start off, unless they happen to have a computer, they'll start off with a dumb terminal, get a flea market, and then if they really like it and get fancy, they'll go to a computer. The thing the computer buys for you is, of course, automation and sophistication. In other words, if I want to connect to a BBS in this network somewhere, we talked about that last week, just like a landline bulletin board system, I can connect. I can say what information you have on there, and somebody's got some information about modifying a 731. I go, oh, I want that. I can download it. Well, if I got a dumb terminal, if I got a printer hanging off of it, I can dump it to the printer. If I don't, I read it, but then what do I do with it? If I have a computer, I can dump it onto a floppy or hard drive and save it, edit it, do whatever I want. I can sit here and talk to 3 different people at the same time, but they're all appearing on my screen together. So if 3 people send to me all at the same time, it'll say like channel 0, such and such a call, some of his text, channel 1, the call, some of his text, back to channel 0. It's all intermixed, see? And you can get pretty good at reading this stuff. I mean, you show somebody this thing, they go, what the heck is all that, see? Well, if you got a computer, you can have Windows. I'm on my channel 0, and all of a sudden up in the corner it says, you got data from WG0N, even sometimes K0PGM. You hit a key, and that window comes up. You type to him, and then it says data from somebody, you hit a key, and the other window pops up, keeps it all separate. If I have a message, I got something for sale, and I want to advertise this around the world, and we talked about you can send a message around the world to the BBS system, I can create my message in my computer, connect to the BBS, and then just tell the computer, okay, shove all that stuff up there. It all goes up there. Goes all around the world through the network and pops out in all these different BBSs. So, I mean, computers are great.
but you don't have to have one to run packet.
Will the network handle binary data?
Yes, the question is, will the network handle binary data? That's the beauty of packet. It'll handle anything that's digital. Right towards the beginning last week, we talked about how it was mode independent. You can send binary files, you can send video. There are people in Boulder right now that are, Boulder, that are sending error-free video. And you don't get little speckles and swatches of lines through your video. It's error-free. They're sending video.
Is that still picture?
It's like slow scan.
Slow scan.
Yeah, it depends on where you're at. If you go up in the higher frequencies, you can run 56 kilobit, 56,000 bits of information per second. I assume you could probably go up to 1.544 if you went high enough. Joe's busy here fixing. This is a typical packeteer, laying on the floor, talking to his equipment, wondering why he's not out drinking and carousing rather than doing this for fun. Right, Les?
Young are looking for the O's and ones that leaked out into the bit.
Right. Blessed are they who talk to inanimate objects, for they shall be known as packet operators. The real problem is the TNC and the computer terminal have to be compatible. This is an interface, and we're going to get into this real heavily here in just a few minutes. Radios, not any real problem. I'm running an old Heathkit 2036, if you remember those. It's got a mechanical relay, and that thing's been banging away for 4 years now in packet, and I don't know how many years before that in voice, and that same old relay is still working. I'm utterly amazed. I kind of like it because if I'm in the other room, I hear click, 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 click. I know somebody's connected to me. So,
you had a buzzer too that went off.
oh yeah, I connect alarms. There are little circuits you can build that beep when somebody connects to you. When I'm on HF, I just watch TV. When I see herringbones, I know somebody's connected to me on 20, so I go down and see what's going on. Radios are not a real problem if you transmit delay. So if you got an older radio, like my old 2036, you want to slow it down a little bit, because otherwise it'll bring it up and then slam the data out, and you haven't gotten to the transmit mode yet. And if you put one bit in error in that packet, you'll never go anywhere.
You know, even some of the electronic relays can't react fast enough to get hold of the packet. That was one of my problems on the one that had the electronic relay.
Mm-hmm.
After you finally get that TX delay set right, well, then you can go ahead and do it.
Right.
I mean, whoever used that digi presently, well, I've got a mechanical relay too.
Yeah. Yeah, they just keep on
I'm
going.
trying to throw a pillow over at nighttime so it don't wake me.
Yeah, right. So anyway, as far as FM, that's about the only thing you have to worry about. If you get onto HF packet, stability is a problem. You have to have stability within 30, 40, or 50 hertz. So the older HF radios won't work on packet unless you want to sit there with your hand on the knob all the time. I run a 757, Yaesu 757 on HF, and I keep a fan on it because I found that when people are using it, it starts warming and drifting, and then when they stop, it goes back down. I'm sure you've seen that with the COLO node. You watch people on the frequency and they drift all over the place. That is a problem we have on HF, is everybody staying on the same frequency. I ran 1200 baud packet. I should be saying with the camera on, but I ran 1200 baud packet on FM on 29.7 megs for about 3 months because there were all kinds of people doing it. And one day I got looking at the regs. I called Les. I put the word out, hey guys, we are illegal. A bunch of people just started doing it. They misread the regs, and everybody else saw it and just joined in. They didn't think anything about it. FM on 10 is great. You don't worry about frequency drift. Everybody's on the same frequency. I'd sure love to see us be able to do that. Oh, we have an OO here too, but that was 2 years ago, Woody.
I think an OO should be outlawed on FM.
Yeah.
So they could frequency, the spectrum utilization. It would take too much space.
No, we kept it within 3 kc. On the TNC, we're going to talk about the digital side. This is analog. Anybody here
not understand the difference between analog and digital? Okay. Analog is tones, AC, pitches, frequencies. It's a varying wave, always changing, usually at a repetitive cycle. Digital is a state. In other words, if I have a digital signal going from here to here, at one instant in time I'll see a positive voltage. The next instant in time I may see a DC voltage. The next instant it may be a positive voltage. The next instant it's still a positive. And then maybe even a zero if it's what's called tri-state. So it's a state, usually a voltage or current as a generality over time. And of course you cannot send positive and negative 5 volts over a radio. And that's one of the purposes of the TNC. Get the next slide. You can look at the TNC as a converter. First thing it does, it converts these voltages, these voltage signals, digital signals, to sounds, so that you can put it out over the radio. It's the same thing as a modem. If you're familiar with the modem, your computer speaks ones and zeros, or positive and negative voltages. But you can't send that down a telephone channel, or you cannot send it over the radio. So a modem converts DC signals to an equivalent AC signal, or tone, analog. That's this thing right here. Digital to analog and analog back to digital, because computers only understand ones and zeros, voltage, no voltage, or different levels of voltages. It's a protocol converter. It converts ASCII, and we're going to get into that in a little bit. Most of these devices speak ASCII, which is a special structure of ones and zeros. And we'll get into that in a minute. To AX.25, which we talked about last week there. In other words, that's packets. If we have any purists in here, or anybody who's really familiar with this, when we call this packet radio, we're really lying. We're sending frames of information, not packets. That means something else special, but it's, for somebody that's really into the protocol, it's not correct. But for us to just use it, packet is fine. So if there's anybody really familiar with it, I just wanted to make sure they understood that what we're saying is not what we really mean if you're really a purist. But anyway, this is just a bunch of characters coming down the line. This is groups of characters, packets. So this is a protocol converter. Anything that comes in here, AX.25, gets changed to the ASCII protocol and then over to the terminal computer. Anything going this way as ASCII is converted to AX.25 and sent out. It's a speed converter. Somebody right in here asked about 300 baud on one channel and da-da-da-da. The normal rate on HF is 300 bits of information per second, 300 bits. Commonly abbreviated 300 BPS. On VHF, if this were a VHF radio, the common speed is 1200 bits per second. Now, on some of the higher frequencies, UHF, you could be running 9.6 kilobits, 56 kilobits, da-da-da-da. The point is, this side of the TNC is running one speed, and this side of the TNC can be running the other. So for example, when I'm on HF, my radio is only running 300 baud, but my TNC and computer are talking at 1200 baud. Okay?
TNC will know that on its own to do that?
Yes. You have a parameter called T-baud, T-B-A-U-D. I go in here, I want this guy to talk at, let's say, 9600 to the TNC. So I type T-baud 9600. Now some TNCs you actually put in a code like you know, code 4 or something. How about your MFJ? Is that T-baud?
You set that with the dip switches.
Okay, that's an actual physical thing. Okay. Okay. The cam Woody, is that T-baud?
You have to look on the file that was A-baud.
Is it A-baud?
You've got ASCII baud. Yeah.
A-baud. Okay. So that's, most of the TNCs have what's called a autobaud routine. On the PK232, when you first turn it on, you type asterisk 4 times. And he knows he's looking for an asterisk, so he looks at it at different speeds. And when he decodes it at a particular speed, he says, aha, 1200. Now, what you're talking to it, you can tell it, T-baud 9600, whatever you want. And then from there on out, anytime you turn him on, he's at that speed. Okay? Then for the radio side, that's on the 232 and PK88, that's H-baud. Okay? I normally run my TNC at 1200 baud because if I'm on the line at 1200 baud, you know, whatever comes in, comes in. And of course at 300 baud, it's a little slower, but it comes here at 1200. You wouldn't want to be 300 here and then running 1200 here because now your TNC's got to buffer it because it's coming in faster and then it's got to slow it down for your terminal. So you don't want to create your own bottleneck. This should always equal the speed of the line or higher.
Isn't there a standard by what frequency you're at?
Yes, that's what I'm saying. HF is normally 300 baud on the analog side up here. You can have this any speed you want because this is doing the conversion. VHF is 1200 baud. UHF, you see 9600. I don't know if there's any 56 on UHF or not. It may be up at 1.2 gigs, but there are 56 kilobit lengths. On 10 meters, you are allowed above 28 megs in the lower end of 10 meters. You're allowed 1200 baud there. And that's pretty good.
So then the term T-baud is just an instruction you give it to make it increase speed or
to set the speed. Now the question is what is the T-baud? When I type T-baud, I'm telling the TNC what speed I want him to talk to me at. When I type H-baud, I'm telling the TNC what speed I want him to talk out to the radio at. Okay? I see a question mark. No question?
Yeah, what you said there implied that the TNC doesn't have to buffer for what the computer or the terminal's telling it. Is that correct? You say it want to avoid having it to buffer stuff coming in from the antenna through the radio.
Oh, it will buffer.
Okay, buffer. Okay, so it buffers either way, right?
Yeah, the buffer is either way. But it's just kind of painful to sit here and have stuff coming in at 1200 and then you're watching it slowly come up on the screen so that you can answer the guy.
So the concern isn't that you don't have enough buffer space.
Well, if you're downloading files, that could be a problem. Now, there's another thing here called flow control. There are two kinds of flow control. Let's say I have a situation where I have data coming in here at 1200 bits per second. And I have this thing set up for 75 bits per second. So my TNC is really buffering because it's coming in real fast and I got to hold it here because I'm sending it out real slow. Well, the TNC will tell the other end, stop sending for a minute. And then when he gets so much of the buffer allocated or free, he'll tell the other end, okay, go ahead and send. And that's the stuff we're going to cover when we get into the protocol. Likewise, let's say that I am downloading a file and I'm really sending stuff to the terminal. And the terminal is buffering as he puts it up on the screen. He can also tell this guy, stop sending for a minute. So he'll start buffering from here, and if it gets full, he'll tell the other end, stop sending. So you have what's called flow control between here and here and here and here. For example, let's say I got a big old file that I've created here and I want to upload it at 300 baud. Well, you know, computers can send this information out real fast. So at 9600, I'm sending data into this TNC and he's sending it out at 300. He will tell the terminal or the computer, stop. And then when he gets the buffer cleared, then he'll tell the other one start in again.
Bill, if you're downloading, can you get it too fast there for the printer to take?
No, because you have this flow control that I'm talking about,
Well, I mean, no, what rate does that printer run at? It's
depending on whatever you want to set it at.
Oh,
You can set printers, parallel printers are pretty fast. Serial printers you set just like you would a TNC or a modem.
okay.
But everything is, if you set up your flow control, then each device has the capability of telling whoever is sending it to it, stop. And then when you're ready to receive more, you say start. It can be your printer, it can be your terminal. So you can have a printer hanging off here, and the data is really flowing into here, and then going real slow to the printer, and the printer will tell this guy stop. He'll hold the data.
So that printer will take it at 1200 when you bring it in there, or so it shouldn't give you no trouble.
Depending on the printer. I mean, a lot of printers can't go that fast.
That's a Commodore, is all I know.
Pardon me?
Commodore 64.
Yeah, I don't know anything about Commodores.
I don't either.
Yeah. Well, I'm sure there's people in here that know something about them. That's why I like to have a big group, because there's enough talent that we can all answer each other's questions, because there's an awful lot to this. The point is, there's two types of flow controls. One is what's called software. It's called X on and X off, or Control S and Control Q. In other words, on a terminal or a computer, if you got data flowing into it and you go Control S, Control key, S key, that's called X off. That tells whatever's sending to you, stop. And then when you're ready to get more, you do Control Q, which is called X on. That sends a character to the device, the TNC or whatever, saying, okay, resume sending. Then there's what's called hardware flow control. We're going to get to that in a minute. You got leads in here. And if you're using hardware control and you want to stop this TNC from sending to you, or the printer wants to stop, whoever wants to stop, he can turn off a particular lead in this cable saying stop. And then when he's ready, he turns it on electrically saying resume. That's hardware flow control. So you got software flow control and hardware. You got to have something on, because the other day I tried to upload a bunch of stuff to Jim and he says, man, there's stuff all over the place. Well, what happened, I hadn't turned on I just loaded a new program and I hadn't realized that there was no flow control by default. You had to enable whatever you wanted. So my computer was just sending it, and pretty soon the buffer got full in the TNC, and then it started overwriting stuff in the buffer because the TNC was saying stop, stop, stop. My computer hadn't been optioned to recognize it, and he had stuff all over his screen. So it's very important. Les, you had a question.
Yeah, the Commodore, I think, is 110. Neighbor of mine's got one. The printer.
Commodore is 110 characters.
Printer
Okay.
and the Epson. Neither one of those would keep up with what flow you can get to come to it.
Okay, so you have to have flow control. Printers are pretty slow unless you've got the the newer ones, and you always want to make sure that you have flow control enabled in your TNC, flow control enabled in your terminal computer, and if you got a printer, flow control enabled there, so that they can all tell each other start, stop, start, stop. Otherwise, if you don't have it enabled in your printer, for example, and you're downloading a file, all of a sudden you'll see pieces of the file just gone. So if you're losing data somewhere, suspect flow control is your problem.
Control Q and Control S, which one is X on?
Control S is X off, S for stop. And then Control Q is called X on. I don't know what Q would stand for in that case. Quick. Okay, your TNC is an error checker. Remember we talked about how we have a means on AX.25 of checking a packet or a frame of data that comes in and determining whether it has errors or not. Okay? We have a crude form of it from here to here that we're going to talk about when we talk about ASCII. So we have error checking going this way. Well, with a cable, you don't have to really worry about errors. You did a pretty bad job of soldering if you're getting errors on your cable. And I have done it. Loose connections, things like that. So it is an error checker. If it doesn't get it error-free, it throws it away. And we'll cover all that later on. CSMA CD. That gets back into the virtual channel thing we were talking about. CSMA stands for Carrier Sense Multiple Access Collision Detect. Aren't you glad you asked? The way this works is these TNCs through the radio look at the channel, and if there's nothing there, they transmit. If there's something there, they wait. And after whatever was there goes away, then they will transmit. And there's a little algorithm in there. When these TNCs hear something and it goes away, they go through a little mathematical process based on a random number generator and then come up and transmit. And the reason they do that is if everybody was to wait for 10 milliseconds of dead time, then everybody comes up at the same time, and then they all come down, and then they all come back up, and you'll be there forever. So when two of these guys come up at the same time, one is always going to beat the other one. And you can go into your TNC and modify these parameters. You can tell on HF you slow them down. On VHF you kind of speed them up. And we'll get into all that later on.
One may beat the other, but as long as they overlap at all, they're both dead, aren't they?
Yes. Now the question is if they both come up at the same time or if they overlap each other, will either one of them win? If I'm sitting here and you come up and Joe comes up, on FM, if you're 6 dB stronger than he is, I won't hear him anyway. But if he comes up and you're 6 dB stronger or more and you come up, then I won't hear him. So the fact that both come up simultaneously doesn't mean that one of them isn't going to get through because of the FM. Now on sideband, on HF, that's a different story. If they both come up at the same time and they can hear each other, nothing gets through.
What's the CD stand for in that expression there?
Carrier detect. Yeah, so the first half of it is carrier sense multiple access / collision detect. And we talked yesterday or last week about most TNCs having a mailbox. Some TNCs, it's a battery backed up, and other TNCs, if you lose your power, it's gone. Now, I've just set up a little program. And my TNC doesn't have a mailbox. So I set up a program in here, and I haven't put it online yet. I've pretty much got it all debugged, but when anybody connects to me, they'll go right into my computer now. And it's going to say you're connected to the mailbox, and it's going to put their stuff on the hard drive, right on the hard drive. So if I lose power, it's still there. Now, let me mention something about TNCs that don't have mailboxes. The older 232, PK232s, the older PK88s didn't have mailboxes. But they've got buffers. So what you do is, let's say I'm going to hit the hammock. It's late, 11 o'clock, and I've had it. I go to my keyboard and I type Control-S into the TNC. I just told the TNC, don't send me anything. Then I shut all this stuff off and I just leave the radio and the TNC on. And then people will connect to me and you have a little message that goes out and says, hi, I'm not here, leave me a message. And they type it in, they disconnect, somebody else connects to you later on, they leave a message. Then I get up in the morning, turn on my computer, I type Control-Q. And that tells the TNC, okay, start unloading that buffer that you got into me. If it's coming too fast, I Control-S it, I read it. And when I'm done, I Control-Q it, and he sends more. So I am, from my keyboard, manually turning him on and off. So if you have a TNC that doesn't have a mailbox, you can have a little message. It's called auto answer. You have, let's see here, C text and C message. C text is your connect text. In other words, what do you want to send to the guy when he connects to you? And I have a little message in mine that says, hi, I'm out goofing off. Please leave a message. It'll save when you disconnect. So they leave the message. And then somebody else connects to me. That little auto answer message goes out. It's called C text, connect text. What do you want to go out when somebody connects to you? And then you have C message on or off on your TNC. If I don't want to, and I don't know why you want to do this, but if I want people to connect to me and I don't want to say anything to them, I just say see message off. But if I want to tell them something, I say see message on. That tells the TNC now, okay, when somebody connects to you, whatever you had in C text, send it out. Is that the same on the cam, Joe? C message, C text, and all that? How about on the MFJ?
Yes, C text and B text is
Okay.
interesting thing to set.
Any questions on this part of it?
I'd like to comment on an interesting one I saw not long ago with a C-text. I connected to the guy and he says, says, I'm talking to your wife while you're playing with this stupid machine.
Well, we're going to take a break here, and then we're going to start talking about the digital side. Before we do that, you brought up B-text. We might as well mention that now. You have two commands in your TNC called beacon and B-text, or beacon text. If you want to let people know you're on channel, then you would type beacon every so many seconds or so many minutes, depending upon how your TNC is set up. And then whatever is in your B-text is what goes out. So you could say B-text is Joe in Denver, something like that. And then when you say beacon every 15 minutes, your call would go out. We're going to look at examples of this when we get in the protocol. But your call will go out, and it'll say something like ID or whatever, and then whatever the B-text is goes out with it. So C-text is what goes out when somebody connects to you. B-text is what goes out when you beacon. Now, you should never beacon any more than every 15 minutes. And a lot of people say every 15 minutes is too often. You see guys in there beacon once a minute, and I mean, they just crash the frequency. And the reason for that is because you can go into your TNC and look at it and see who's been beaconing. So if they beacon once every half hour, it's going to appear on your screen if you go look. You don't need them to beacon every 1 minute and this sort of thing. So if you're going to beacon, half hour is probably the good recommendation, really. Les?
A lot of times you've got traffic going and you don't want to beacon at all.
Yeah.
You reminded me how to get to this one. I can't do it myself again, but it will beacon every 15 minutes after it hears the last signal. Otherwise, if the channel is busy, it will never beacon.
Yeah, not all TNCs unfortunately work that way.
15 minutes after it hears the last signal, then it'll send out a beacon.
The cam you can set up that way, where while there's traffic it won't beacon, and then after so long of silence it'll start the timer and then it'll beacon. The PK232, if you say every 15 minutes, when that time comes up, as soon as he hears a clear time, he will beacon.
You can do that on 232 though.
Can you?
Yeah. I had a problem with mine where, every 15 minutes, I hear what you're saying, but it gives you, at least on the 232, you can set it lower than that if you want to. And for some reason, when I was just testing my beacon the other night to see if it worked, I wanted to set it lower so I could just see whether it was, without waiting.
Oh, you mean, yeah. Okay.
And I couldn't do that, and I called AEA, and they thought maybe it was something that came out in the last EEPROM or something, where you can't set it any lower than 90 anymore.
Okay, well that's something different, because I have set mine down to every 5 seconds when I'm doing TVI checks and all that. I just set it on some obscure frequency and let it beacon every 5 seconds, and then go up and start playing with filters and whatever. But I have an older version of 232.
Yeah,
I would like to see them put that in there, because...
I'll bet they did in the August 91.
Maybe they did, because mine's 87 or something like that. Yeah. Any more questions in the coffee break? I know you all discussed all this in depth. And
just one question, Bill. Why is it that people beacon in the first place?
Okay, the question is, why do people beacon? It depends on what you're... Yeah, proud of their call, you betcha. It depends on what you're trying to accomplish. Some people leave their radios on all the time, so you know they're there. Other people beacon messages we have one fellow on 2 meters that beacons through the gateways and onto HF, and he's looking for chess players. So he beacons every half hour. Chess players, please send me a message at my home BBS or contact me here. I sit on 2 meters a lot, and I beacon through W0TX out on 20 meters to California, and then through his 20-meter node back to 2 meters, so that friends of mine in California, when they see my beacon appear on 2 meters there, they know the band is open between us and they connect to me. So there's all kinds of crazy things you can do with beaconing.
Propagation.
That's a good one.
Yeah, propagation. We'll get into this a little later on, but all my ideas of propagation and how it works went out the window when I got into Packet, particularly HF Packet. I've learned a lot. Okay, next slide. This is the eye test. We were going to enlarge this after the last class, and I don't know what happened. We forgot. Anyway, again, this is a different view of that slide we had before, this one. This is the analog side to the radio of the TNC. This is the digital side. Okay? Now, to connect a TNC to a radio, you have, is it my eyes or did that just change focus? You have audio to the mic jack. Now, if you have some of the radios that have like phone patch audio in, audio out, you can feed it in back there, that sort of thing. So anyway, you have audio that goes to the mic jack. You have a push to talk that goes to the radio. Again, usually the mic jacks. If you have some of the radios that have all the jacks in the back, you can feed it in back there. And then anything that comes in via the radio comes out of the speaker jack into the TNC. And then you have a common ground. So when the TNC wants to send something out, he turns on the push to talk. After that TX delay interval we talked about, he then sends the audio out to the radio and out over the air. He turns off the push to talk. Signal comes back in, comes out the speaker jack, earphone jack, whatever you want to use, phone patch out jack, into the TNC. So that's basically the only wires you'll have. Sometimes it gets a little tricky here because, for example, an ICOM 2AT, HT, the audio and the push to talk are common, so you got to put a little capacitor in there. So most of your manuals on your TNCs will give you little lash-ups, wiring arrangements for this area here if you have a radio that doesn't have separate audio, separate push to talk. So no matter what kind of a strange radio you have, there's probably a way of getting it to work with a TNC. If it turns out you don't have this kind of arrangement. On the DC side, the digital side, you have pulses, which represent data going into the TNC. When signals come this way, you have pulses coming out of the TNC. This is the basic interface. It's called RS-232 is the terminology for this. It defines a lot of things that we're going to get into here in a minute. Basically, it defines the functions of the various leads in the connector from here to here. That is a standard interface that most computers use to talk to modems that we talked about earlier. In other words, if I had a phone line here, then this would be a modem. I have pulses here, analog here going out on the phone line. So the TNC is acting as a modem or a digital to analog converter and vice versa. Question?
Don't know if any of your computer experts, but what is the difference between just the standard 232 connection and what they call a null modem?
Okay, a null modem cable. Let's get into the wiring diagram of this thing because I'm going to discuss that. Okay, don't let me forget. what is a null modem. It's just the way the leads are handled here.
But on
Okay.
the standard 232, does both ends of the cable or send data?
Well, let me go wait until slide after next. I have a picture of it, and then I think you'll see what we're talking about there, because we're going to cover all the leads in this interface. RS-232 says that I have a set number of leads, and lead 1 is going to do this, lead 2 is going to do this, lead 3 is going to do this, lead 4 is going to do this. By convention, it's a 25-pin connector that we're going to look at. But that is really not part of RS-232. It could be a 9-pin, it could be a round one. The actual connector is not defined, the shape of the connector, but by default or convention, it's either a 25-pin or a 9-pin connector. And we're going to go through each of the leads and how they work normally, and then when you have a null modem cable and some of the tricks you may have to do. Joe is having to do one on this one tonight, as a matter of fact. So make sure I answer your questions on that. Rick, anything else I need to mention on RS-232? He's one of our data guys. Keep me honest. Okay, you remember earlier I talked about ASCII to AX.25 protocol conversion in the TNC? Okay, we're going to talk about the ASCII protocol, what it is. Then we're going to talk about the RS-232 interface, and then we're going to start into the AX.25. If I can have the next slide. This represents the snapshot of an ASCII character. Rick, you've been in data a lot of years. What is that?
Oh, the character?
What character is that? Did you bring your handy-dandy decoder?
No, I didn't.
No, you didn't. Okay. I thought maybe some of the old teletype guys used to be able to take the tapes that had all the holes in it, and they were Baudot, and they used to be able to look at the holes and read the tape. And I thought Rick could read these things. Anyway, this is looking at one of the wires on that RS-232 interface. Let's say it's the wire going from the terminal to the TNC, or the computer to the TNC. And the guy at the keyboard hits a character. In this case, it happens to be a capital Y. I take a snapshot and I see these pulses go down the line. In other words, I'm looking at the wire, and these are time intervals. Let's say 100 milliseconds. Depends on your speed. The higher the speed, the narrower these are. I'm going to see a positive voltage, then I'm going to see a negative voltage, a positive voltage, a positive, negative, negative, positive, etc. It takes these 10 pulses to convey the capital Y character plus some other information. The actual character is these 7 bits right here. In other words, if bit 1 was a 0, then it'd be some other character. But the TNC knows that if I see a 1001101, that's capital Y. If I see a 00011101, forget that 1, that may be a Z. They have these charts. You could decode it if you wanted to. So ASCII protocol is a character set built around 7 bits. Every time I hit a character, there's 7 bits of information that's going to go out. If you use powers of 2, that means I can have 128 combinations of 1s and 0s. I can start off with all 0s for some character, and then 1 and all 0s, and then 01 and all 0s. But I can come up with 128 different combinations of 1s and 0s in 7 bits of information. Does that make sense to all you math majors out there? Anyway, that's what ASCII is. ASCII protocol says that I have defined 128 different sets of 1s and 0s to convey 52 upper and lowercase characters, 10 numerics, 0 through 9, 33 control codes. Remember Control S, Control Q? If I hit Control S, some predefined set of 7 bits goes to the other end, and the other end says, oh, that's Control S. So I can have 33 control codes, or 33 symbols, you know, backslash, ampersand, pound sign, and all that. So that's the ASCII character set, 128 different characters.
Is this different if you're sending binary? I mean, the way you lash them together?
Binary says that I am sending a group of ones and zeros that in themselves are meaningless. In other words, if I just send 8 of them or 7 of them, it doesn't mean a whole lot. How can I best define that? You have ASCII, which is 128 predefined character structures. You have EBCDIC, which is 256 characters, because I am using 8 bits of information. And I have to put something around these 7 characters to define these characters. I'll get into that in a minute. Binary just says I'm going to send a whole string of ones and zeros.
Is there checking?
Yeah. I don't want to get too deep into that, but the actual protocol, when you transmit binary, the protocol is going to check it, and we're going to go into that part of it. Rick, how would you define binary? Binary transfer, not binary bits, you know, 1 zeros off on.
I guess just a series of ones and zeros.
It's just a whole series of ones and zeros.
They're not attached, they're not coded by any alphabet or anything. No,
there's no... The thing that's the application that's sending it and the application that's going to decode it knows what it is.
It's compiled information.
Yeah, you know, if you take a program, if you've ever done any programming and you compile it and then you try to read it, your terminal goes nuts because it doesn't know how to handle all these ones and zeros coming in. I saw a hand up over here.
Is ASCII the way the packet is sent or translated between the TNC and the computer?
The ASCII information will be. I'm going to get into that. I'm going to show you how it's going to work. Right now, we're just going to send it to the TNC, and then we're going to explain how it goes from there.
If so, does that mean that a TNC bought in the United States would not work in Germany or Japan?
No, not at all, because remember I was talking about on AX.25 to begin with, you can send binary files, which is just ones and zeros, meaningful only to the 2 applications. I can send this EBCDIC, which is 8 characters, or I can send video, again, which is a bunch of ones and zeros. The TNC does have to know if you're using something other than ASCII. For example, if you watch 2 Japanese stations on 10 meters talking, you'll get the to from address, the to address, the from address, and when you look at what's in between, your terminal goes nuts because it's...
But that's what you said last week. But could you adjust your TNC to
No.
the characters?
I'd have to have a ROM that could do that. Our TNCs, and basically worldwide, are set up for ASCII.
But does that mean you cannot talk to an English-speaking Japanese person in Tokyo by packet unless he...
Well, if they're using the standard TNC, which most of them do, yes. You don't see that many. You don't see that many people talking foreign languages. Well, when I say foreign languages, you see Spanish. I connected to a fellow the other day in Brazil, and he started typing all this Spanish to me, and I called my son down. I said, "What's he saying?" Because that's still ASCII. But if they have a character set in their language, like the Japanese or Greeks, you know, that's just like a computer or a printer. It has to be set up for that character set. Okay? So your TNC is going to think it's binary and just ship it out to your screen as binary text. But your screen, your computer, your terminal isn't going to be able to decode it. Your bell's going to ring, the screen's going to clear, cursor's going to spin around, all kinds of wild things. So anyway, basically we're going to when we talk from the computer to the TNC, we are going to take our ASCII character, capital Y, put some information around it that we're going to talk about in a minute, put it into the TNC. The TNC is going to strip off all this miscellaneous stuff and take this information and put it into your AX.2 frame and send that out. In other words, the protocol conversion is I take the ASCII protocol off, take this piece of information, the capital Y, put it into my AX.25 frame, put all that protocol that we're going to talk about around it, you know, the to address, the from address, what kind of a packet is it, and ship it out. Remember I talked about last week how the reason they call it packet is because I take my information, this capital Y, I put it in an envelope, I put a to address, a from address, I number it, and then I mail it. That's what the TNC is doing by converting protocol. It's taking the information you're giving it, be it ASCII, be it EBCDIC, be it binary, takes all the protocol dressing off that information, puts the new protocol dressing, AX.25, and sends it out. I think you'll see that when we get deeper into this, because we're going to look at the inside of a packet where we'll see this stuff. Anyway, so we got this capital Y coming down the wire. Remember I said there was a thing called error detection in ASCII? Somewhat crude, but it works. That's this bit here called parity. Now the reason we're talking about all this stuff is because you got to set your TNC and your computer up so that they talk the right parity, the right number of data bits, the right number of stop bits. That's why we're going into this, so that you know how to set up, because that's a very common problem. I don't know how many calls I've gotten where I get garbage or I don't get anything. Say, well, what do you have your data bits? What do you have your parity? What do you have your stop bits? And that's been the whole problem. Very common one. We kind of got that problem with this thing here. This computer is looking for some weird things. But the master is at work. But he's still not smiling, and it's been an hour now. Anyway, this bit is the error detection bit. In TNCs, in computers, and modems, and in RS-232 type printers, you can select the type of parity you want. Do I want even parity, odd parity, no parity, mark space parity? Now, what all that means is, if I pick even parity, then that tells the device that's sending that I got to take a look at the number of ones in the character. And if it's even, in this case it is, I got 4. 1, 2, 3, 4. I put a 0 there. If it's odd, let's say that was a 0. So I only have 1, 2, 3. I'll put a 1 there, so that I always have an even number of ones between this bit and the 7 data bits. Let me say that again. If I set this system up for even parity, we're telling the sending unit to count the number of ones in these 7 data bits that represent the character, count them up, and if it's an odd number of them, put a 1 in there. If it's an even number of them, put a 0 in there, so that between these 8 bits, I always have an even number of ones. If it's odd parity, then I just do the reverse. Now, theoretically, what happens is the receiving end knows, because he's been told also. You told TNC, even parity. So he counts them coming in. And let's say that that got changed to a 1 because there was a burst of noise. He says, 1, 2, 3, 4, 5. Uh-oh, something's wrong. I got 5 ones. I'm only supposed to have 4. Or I'm supposed to have an even number. Okay?
So parity again will be a 0 if even, a 1 if odd?
No. He counts the number of ones in the 7 bits of the character. Disregard that. Disregard this. He counts the number of bits. If there's an even number, he doesn't add 1.
He being the CAN. The CAN does the inserting.
Whatever's transmitting the character, the computer, the TNC, the modem, whatever is creating the character. When you hit the W, or the Y in this case, he says, okay, that is this bit structure here. It's a 1001101. Now, let's see, I got even parity. Do I have an even number? 1, 2, 3, 4. Yeah, I got an even number, so I'm not going to put another 1 in there because that'd make it an odd number of 1s. In other words, when you define parity, you're saying that